Hey, how's it going? We are doing Codeforces Round 860 here. Alright, let's get started. Hey, and it's Max, and you can swap AI and be. Oh. Okay, well, one of them has to be the max of everything. Sure, I know what to do. Okay, so. Read A first. Alright, if A, back. Oh, really? It's. Okay, I see. That's actually all you're doing. So. Okay, that is fine. Afterward, okay. Okay, you just go in reverse and you pick anyone who's never been seen before. So pick 1, pick 9, pick 8. Sure, okay, that's it. Those are just out vector. Oh, great. Everyone's next. Oh, if. Okay, great. Keep going. B icons. AI type of type I. And everything in a pack. number in one pack. Okay. Oh, AI is kind of big. What's the maximum of divisors? A 9-digit number. 1344. Well, that's a little bit annoying. You only care if you can make them equal. Okay, so you have a bunch of B's. You have a bunch of B's, and then you have a bunch of A's. You need to pick a factor for every A. And as many of them to be equal as possible. The D ratio is like the opposite of the V ratio. So the D ratio is the opposite of the V ratio. Oh, you can just you just take BI times AI. This one, you take their GCE. And then beyond that, you can divide out anything you want. You're just greedy? I think you just greedy it. It's okay, interesting. You also keep the running DC of the A's, or the D's rather. Of A's and B's. stick to N64. If running GCD mod before device and AI mod after device, then we can maintain it. And then if we can maintain it, what we do is otherwise we failed to do it, and so we're just going to keep it's just a greedy. Okay, let's do D. Sum 0. Okay. Well, the sum is 0. Okay. Yeah. It never exceeds the range. There's some no's. Oh, not only. Oh, just less than, not even less than or equal to. To all zeros, it's not possible. Yeah, don't you just greedy the prefix sums? If it's less than or equal to 0, you take a positive. If it's greater than 0, you take any negative. Come on, this can't be that hard to compile. Okay, and now Probably should have done this first, if it's this easy. Okay, great. That was much easier than C. Wow. All right. Oh, what? Each element of your must be exactly one subarray, so it must consist of consecutive elements. Non-negative so that it becomes a multi-test. Find f of every suffix. Okay. Right. Okay, sure. Okay. That's E. Two wrong smiths. Oh, he would have been ahead of me. Alright, well. Well, you only have to replace at most two, right? Because you could just replace it with one and then m minus 2 or whatever. 1 and then m minus 2. So 2 is, so you just want to know, okay, so first of all, yeah, is it 0? Oh, for each suffix. For each suffix, is it 0? And then for each suffix, is it 1? Otherwise, it's 2. For each suffix, is it 0? Well, you can just see, like, jump. Oh, you can just calculate how far to jump. From here, you jump to there, and then if it works. Otherwise, it doesn't work, it's a one. Is it 1? Is it 1 is the key question? Just change the first number, or you can change the... Yeah, so all right, we should start by calculating these jump. That's for sure. still a case problem? This is not a case problem. If it's equal, then it just takes one jump. Otherwise, we failed. Plus one. Maybe we should use infinity. Because then plus one is 5. If I plus AI is at least n, if they're equal, they go exactly. Sorry. That's not what I want, is it? I plus AI plus 1. Oh, that's weird. Yeah. Okay, so let's try this. Two, one, and bad. 2, wow. 3, wow. Bad. 2, 1, bad. It's kind of cool. Okay, so okay. So we've got everything as 2. We can figure out if it's 0, and then we need to figure out if it's 1. It's 1. Okay, actually 0 is quite easy. This, it's so easy. AI equals jump. Oh, right. They don't even have a 2. I don't know why that is. Oh, they have a 2 down there. Okay, so yeah, we figured out the zeros. Zeros are easy enough. All right, now we need to figure out the ones. I guess we have this. If jump I plus 1 is less than infinity, then it's equal to 1. This is probably better. I don't have to keep nesting further. To 1. But that means we can just change our first number. And then if we cannot change our first number, we're going to have to go for a while. Then replace, and then do something here. Oh, that's really weird. So we need to... Okay, it's definitely tougher. Yeah, it's this last case that's the hardest. You have your number, go here, jump, 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 and then at some point you decide to break your jumping and you just grab something to the end. And you're looking for 3 here. What's the last 3? What's the last? Yeah, so I guess we can start by computing the latest, because we're going to use that anyway. You can also just go to the end. The jump end is 0. What about you do this? Alright, so we have latest. So now what we are looking for is, so let's hit 7. So here, or like, do we want to replace this number? Well then, if the latest 6 is after us, what is your TR jump? Is the latest 5 after us? Are we less than the latest 5? And so we have a sequence, and we're comparing that sequence less than latest 6, less than latest 5. We'll just keep this point there and we're done. Less than latest 4. Oh, but the latest array, it has to be, the latest array is decreasing because I don't know how to finish this last part. Oh, you can do like a binary search, or like it's like a binary search almost to know. Oh, I know. It's like a suffix. Okay, so you just do like a vector int. The max. It's like the max. Max grader. Yeah, you just binary search within. Okay, so for myself, I want to know. Yes, I'm like for myself, I want to know. Yeah, and then here, okay, so I. I'll find the first thing that's less than or equal to, but we want the last thing that's greater than, so yeah, -1. Okay, so -1, max grader I is going to be and then if I plus AI plus 1 is less than n, I think that's what we're looking for. And then this is going to be like if is at least. Really? See, I don't have a ton of confidence. So I think this is the wrong answer. I think I need to do one more thing. Or do I? No, maybe I don't. I don't. This is it. Transfer to minus 50. Come on, hurry up. Sweet F. Okay. Oh, a little slow. Okay. Why is it n plus 1? Whose idea was that? Alright. Exactly. Okay, yes. In the boxes. Oh, okay. Okay, so you should be able to do all of them except one. The last one, I mean, what is a million for? We don't need that many. We only need like a 200-ish. So you do 7, 7. Oh, it doesn't matter. So they buy. And then 135 is a multiple of 3. Yeah, sure. Say. Cannot change the order. We just need to, we just need to solve k minus 1 of them, and then the kth one you just solve. It's fine. Maybe it's always possible. Maybe that's why there's no -1 case. Some greedy approach? You just get it? It's just a math problem or something? Right, okay, so you have a bunch of box values, and then you have a bunch of numbers, and one of the numbers is always at most half. Okay, 4 and 5. Or for 7, you can have 4 and 4. Okay. You can have 7 boxes, and then you have 4 and 4. One of them is almost half rounded up. Okay, and then do you just knapsack to find it? Okay, I think we'll just go ahead. Let's just go ahead. The runtime is not a problem, right? Given n, if you have two n minus one numbers, you can find n of them that have to multiple of n. I think that's a claim. Shouldn't people be done then? Interesting. Should I try to prove this claim? Okay, well, it's true. Cool, let's do it. Let's do it. Yeah, it's just, and then after that's just like a bunch of reconstruction. And how do you find it? You need to like. Is there an easier way to find it than just knapsack it? Oh, okay, whatever. Let's just find that, yeah, vector int. Oh, is this too slow? Like what? TP000 is true. It's not like the copying matters at all. Okay, so let's do that. Let's do this. First of all, you can just skip it, and then oh, vector pool is annoying. Let's just do this. dp I plus 1, x plus 1, s plus a mod k, or equals dpi x x. It's cubic. This is the DP for, and now we need to reconstruct the subset. All right, now we're gonna start from end, and we're gonna be like, if dp n minus 1 count sum if dp n minus 1 count minus 1 sum minus a plus k mod k. This is actually n minus 1 count minus this should be like assert false. Or rather, one, two, 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 1, 2, 2, 3, 3, 4, 0, 2, 3, 4. Yes, wow, that's pretty good. Okay. Wait, so just repeatedly call this, right? We can do this. Zero, 2, 3, 5, right? Yep. Okay, great. That seems to work great. Now we're gonna do. We're just gonna do S0. This should be a pair. Now that we have that, we're just going to go in order. Okay, so we're just going to go in order. We're just going to assign the indices. Okay. So that's it. Yes, and now box indices K is that you just do this, right? Find subset A, and you're going for the size of S. Your size is S, and then yeah. So now we're gonna do. I'm just gonna blank these out. Back I, and then we're taking a sum. The last number we need is that's my sum. So that's our last number. Need. Great. Okay, so now oh, you don't do the last. If K equals break. Six, 1. Oh, we missed it, but I think we're ready. Okay, so break, that's 15 milliseconds, huh? Interesting. All right, nice. All right, I'll come back in a little bit. All right, everyone, contest is over. We did indeed get third place. And all right, I'm just gonna talk through the problems and the ideas real quick, just like a high level overview, not gonna go too in depth, but basically problem A, you've got conditions you want to satisfy. A(n) is the max of the A's, Bn is the max of the B's. The only thing you can do is swap AI and Bi. So let's just assume that Bn is the bigger one out of An and Bn without loss of generality. Then Bn has to be the biggest number in both of the arrays combined. So in that case, basically we can greedily make sure that between AI and Bi, we always put the bigger number in Bi, because Bn has to be bigger than everything anyway. And so that's just the approach. You just do that. If AI is greater than Bi, swap them, and then you just check the condition described, and that's it. Print yes or no. So that's A. Problem B. Problem B, another greedy idea. Basically, the lottery winner on day I is not allowed to participate in the lottery after day I ever again. Yeah, so another just greedy problem. You actually go backwards, and then what you do is to pick the lottery winner for day I, you just pick anybody who has never been seen before. And remember, going backwards, so technically we're picking anyone who does not show up in the lottery afterward. And between multiple choices, it doesn't matter who you pick. Regardless of who you pick, none of them can be the winner before that, because they all show up that day. So that's all you really have to do. So I just go backwards, set my winner variable. And I use a set. If this is a new person that I've never seen before, then we set that person to the winner. Otherwise, if we don't find a winner for this, we output -1. And if we do find a winner for every day, we can output that. That's B. Problem C. Problem C is another greedy problem. This one's a bit of an interesting idea. So we're just trying to maximize the number of adjacent pairs where they end up being equal. That's the same as minimizing the number of price tags, because the number of price tags is just n minus the number of equal pairs, adjacent equal pairs. So yeah, essentially we're just trying to see, if we just go left to right for each one, we kind of check, can we make this equal to the previous one? And the way we check that, and we actually have a run of equal things, and so we only want to make it equal if we can make the whole run equal. So the whole run needs to get one longer. If the run cannot get one longer, then we can make, I and I minus 1 equal, but then we break an equal pair earlier, and that's not worth it, because we'd rather have more freedom on I. So yeah, basically what we do is we just keep track of some like summary values of our run. In particular, we want to know what is the last A value, and then what is the running GCD of the whole, basically the GCD of the whole run. And so here we're just checking what's the before value, what's the after value, take the GCD, which is the largest number we can make them equal at, see what we need to divide by on both sides, and then we just check, can we divide the running GCD by this, and can we divide AI by this? If so, we can extend our run, and let's do it. And if not, we just start a new run here. So pretty simple, like greedy idea. Just take some GCDs. So this is like n log input sizes. And so this is fast enough. Let's see problem D. Oh, problem D, I thought this was much easier than C. Basically, you end up just, you're trying to make it so that the max absolute value of any subarray sum is less than the array max minus the array min. And then the way to think about this is just if you take the prefix sums, if you consider all of the prefix sums, the biggest prefix sum and the smallest prefix sum, the difference between those two is going to give you this value. So the difference between the smallest and biggest prefix sum has to be at most this. So what you can just do is we can just set up our order so that the prefix sums are always between the max value and the min value. And in fact, you can explicitly avoid the min value. And so that's what we do. So basically the idea is just sort the numbers we get. If everything is 0, then it's not possible because it's not less than, it's equal. And then otherwise the answer is yes. And basically we just take our current sum. If our current sum is less than or equal to 0, we take a positive number and we add that. If it's greater than 0, then we can take a negative number and we add that. And so the idea there is if it's less than or equal to 0 and we take a positive number, we'll definitely end up at most at the max value. And if we're greater than 0 and we take a negative number, we will stay greater than the min value. We can at worst hit min value plus 1. And so that way the range stays in here like we want, and it just works. All right, problem E. So I thought this was the hardest problem. Basically, if you want to turn something into a multitest, you can always do it with at most 2 changes. You can just change the first number to a 1, and then you change the second number to the length of the test. So 2 is always the worst case answer. So we're just trying to check for every suffix, is the answer 0, and then check if not, is the answer 1. So the first idea is to create this jump array, which is starting from here, assuming our current position is a test, and we keep going further and further. How many jumps does it take to get to the end, or do we fail to get to the end? And so that's what's going on here. If we go past the end, it's infinity, which is fail. Otherwise, it's just the jump of whatever comes after our test, plus 1. And then to check for 0, it's just, is AI equal to the jump of I plus 1? So that's a pretty simple one. And then another version is if jump I plus 1 is valid, it does reach the end, then the answer can also be 1 because we can just change the number of tests in our multitest. And then the trickiest case is can we change one of the test sizes to make it valid? And there's some details here. Basically, you want to take the regular test for some while, and then rewrite some test number, go somewhere, and then jump to the end with the right number of tests. So there's just kind of a condition. It's like this, is this index less than something, or is this index less than something? There's some details in there. I won't go into detail, but basically you can end up computing this max suffix value and then use that value to check this condition in O of 1 here for this. And this is a binary search. This is actually not necessary. I think you can just, yeah, this is not necessary because we're just searching for I. So we can just do a 2-pointer sweep and then the whole thing is O of n. But anyway, that's problem E. Finally, problem F. Problem F is like a cute one. So basically, there's a key fact here, which is that if you have 2n minus 1 numbers, you can always find n of them where the sum is divisible by n. And you can look this up, just search around for it. There are some proofs online. But that's a key fact. So by using that fact, we can find that it is always possible to solve this. And then basically, we can just take all of the s values, but the biggest one. So the key idea is once we assign the boxes, then all of the classes have to be solved except for one, which is missing a box. And the one that's missing a box, we can always pick a number to make it work. Because all we have to do is make the sum divisible by that s of I, which is going to be at most 201. And so we can just pick the right number mod that s to make it work. We don't even need 10 to the 6. Even like 201 would be enough. And so we just need to make every class except one work. And the way we do that, we just pick all but the biggest class, and we just almost like, you can pick any order you want because of the lemma that I mentioned. You'll always be able to find a subset that adds up. And so after that, it's just some details. I use knapsack in order to find the subsets. And basically, yeah, just sort the S, take everything except the biggest one, find the subset, assign it, and then finally you take the last number, figure out what you need to make the sum work, put that number in, that's your new number, and then you just set it up. And so this is like cubic runtime, so it's very fast. Okay, cool. That's it. I'm gonna call it a day for this one, but thanks for checking this out, and I'll see you in the next one.